Okay, in the second half of this video, I want to focus on what we would call rational expressions. Now, a minute ago, we said that a rational number is the quotient or the fraction of two integers. A rational expression is a quotient of two polynomials or two expressions. Each of these are an example of a rational expression. Now, this looks like just a regular rational number, but that's okay, because as we said in a prior unit, a polynomial can consist of just single numbers, which we would call a monomial or a constant monomial. Each of these other examples are what I would call expressions or polynomials. We can write an expression or polynomial for the top and the bottom of the fraction, and when we divide those two, or when we create a fraction out of both of those expressions, one top and one bottom, we have a rational expression. Now, the trouble we run into is that anytime we divide by 0, that's what we would call an undefined result. The result for division by 0 is not defined in our current level of mathematics. So we would run into a problem if the denominator of these rational expressions ever ended up being equal to 0. Now, in these first two cases, there's no way for the number 4 to be equal to 0 or the number 7 to be equal to 0. As soon as we apply a numerical value to the denominator, then that's it. It can't be anything else. But in the next few examples, we have a problem. 2 times x, 4 times a times b, y squared minus 5y plus 6. Any of those could potentially equal 0 if the variable itself took on the proper value to make that denominator equal to 0. So here's what we mean by that. In that middle example, x plus 5 on the top divided by 2 times x would be undefined or has no meaning if x itself was ever equal to 0. X is a variable. It can take on different numbers based on what we assign to it. And if we assign this x to be equal to 0, then that's a problem because 2 times 0 equals 0, and now we have the fraction 0 plus 5 divided by 2 times 0, which would be the fraction 5 divided by 0. Our b value is now 0. It's undefined. Any other number for x would be just fine, but when x is set equal to 0, that's when we have a problem. Similarly, in the second example, a squared minus 1 over 4ab, that would be undefined or have no meaning when a is equal to 0 or when b is equal to 0. If a was equal to 0, we'd have an expression that looks like this. 0 squared minus 1 over 4 times 0 times whatever b value we choose. That ends up being negative 1 over 4 times 0 times b. Well, if you remember the zero product property, that states that 0 times anything becomes 0 itself. And now again, we have a negative 1 divided by 0, 0 in the denominator, which is a problem. If b was equal to 0, we'd have an unknown a value, a squared minus 1 divided by 4 times a times 0, and we run into the same problem. Even though I don't know what a is, I know that the denominator ends up being equal to 0, and we can't have that. It's an undefined result. Lastly, our final example here, y minus 2 over y squared minus 5y plus 6. We should recognize that this denominator, this quadratic in the denominator, can be factored into its binomial pairs, y minus 2 and y minus 3. If y ever took on the value of 2, we'd have a problem because 2 minus 2 ends up equaling 0. And regardless of what the answer or the expression simplifies to on the right-hand side, this 0 that we get here multiplied by this result turns the entire denominator equal to 0. So we have a problem when y is equal to 2. And similarly, if y was equal to 3, we'd also have a problem. 3 minus 2, that's not any trouble for us, but 3 minus 3, that's going to cause a problem. If these y values ever change to the number 3, that produces an issue. This 3 minus 3 creates 0. That 0 times the remainder of that denominator also changes to 0, and we have ourselves a problem. So as long as y is not equal to 2 or not equal to 3, then this expression is totally fine. We can use it for however we need for all values except for 2 and 3 in place of y. So let's look at this expression, 2a minus 5 over 3a squared minus 4a plus 1. For what values of a is that undefined? Well, again, we're looking for denominators equal to 0, and we want to know if or when that's going to happen. So you could sit here and try to guess what a values would make this denominator equal to 0, or we could use the techniques from earlier in this class. Now, some of you did fine with the factoring methods, and you could probably factor this. This is what I would call a standard trinomial with a not equal to 1. So you could try factoring this if you want, or we can use the tools from our most recent weeks in class and rely on our quadratic formula. So if we say that QFP and QFM are used to calculate the values, let's see, QFP using an a value of 3, a b value of -4, and a c value of 1. That should produce one of our results. That would be off limits, and then 3, -4, and 1 in QFM, that would produce the other result that's off limits. And when I say off limits, I mean that would be the number that makes this expression undefined. That would create a 0 in the denominator. Now, I used my calculator off screen, and my QFP calculation came out to be the number 1, and the QFM calculation came out to be 1/3 or 0.3 repeating. So that tells me that the value of a that makes this fraction undefined would be 1 or 1/3. Now, some textbooks and even Math Excel might prefer to see their answers written this way. We would say that a equals 1 and a equals 1/3 would make the equation undefined. Another way that we can report this too is we can say that a is not equal to 1 and a is not equal to 1/3. That's our way of saying that this expression can be used for all a values as long as a is not 1 and a is not 1/3. So pay close attention to how the questions are being asked in the context that you're working on, and you can decide which method would be appropriate for you. Now, for these next 3 examples, we're going to work on simplifying again just a little bit, and we'll come back to talking about excluded values. In question A, if we're being asked to simplify, we want to reduce this to lowest terms. One of the tools that we utilized was expanding these values and looking for common factors. So in the numerator, there's nothing to expand. 2 can't be expanded, x can't be expanded, so I'll just write it as 2x. But 6, on the other hand, that can be expanded into 2 times 3. Now, the 2's are technically separated by from the rest of their terms by a multiplication sign. And when we've got terms that are separated by a multiplication sign that exist in the numerator and the denominator, they can be factored or canceled. And now we have the 2's gone, and we're left with an expression x over 3. Similarly, in part B, I don't think there's any factoring for us to do, but we should note that between each of these terms, 3a and b is a multiplication sign. And between a and this term is also a multiplication sign. So I've got basically 2 items that are multiplying here and 3 items that are multiplying up here. We can get those components to cancel as long as the terms are separated by multiplication signs and exist exactly the same in the numerator and the denominator. So I see this a and this a exist in the numerator and the denominator, and both of them are separated from the remaining terms by multiplication. So that leaves us with a term that contains a 3b in the numerator and a term a minus 1 in the denominator. Now in part C, we have a y minus 2 in the top. Nothing can be factored there. In the denominator, we could use our quadratic formula to find our excluded values, which in turn could help us with our factoring. Or we can note that this is a standard trinomial with a equal to 1. So by reporting y, and then I would say 2 and 3, y times y regenerates the y squared, the 2 times 3 regenerates the 6, and if I go with a -2 and a -3, then in the process of this distribution, -2 plus, or I should say -2 minus 3 here, also produces our -5 while still multiplying to make the +6. So this is the factored form. Now this numerator has a single term, the y minus 2 term, and the y minus 3 and the y minus 2 terms in the denominator are separated by a multiplication sign. So what's interesting is that this term, y minus 2, also occurs in the denominator, and those are technically separated by their adjacent terms with a multiplication sign. Up top here, I'm just including a times 1 to indicate that we can multiply anything by 1. Treat the number 1 as a separate term. And now the y minus 2's have canceled, and we're left with the fraction 1 over y minus 3. And we've reduced option C, we've simplified it to its lowest term fraction. And we've got two more examples here to finish out the video. In this example here, 3x minus 12 over 3x, we should be on the lookout for ways to factor the numerator as well as the denominator, but as it turns out this time the denominator can't be reduced, but the numerator can. Do you notice that there's a GCF in the numerator? That's one of the first things that we look for when factoring is a GCF, the greatest common factor. What number can divide both 3x and 12? Well, as it turns out, it's the number 3. So if we factor out the number 3, we're left with an x in this first term. And if we factor out a 3, we're left with 4 in the second term. And there was a subtraction sign to separate those two terms. So we'll call this 3 times the quantity of x minus 4. Now here again, we've got the number 3 separated from another, what we call a binomial term by multiplication. And here this 3 is separated by its monomial term by multiplication. When we have terms that are separated by multiplication, if they exist in the numerator and denominator, they can cancel or factor each other out, or factor down to the value of 1. And this leaves us with the expression x minus 4 over x. Now remember, the reason why we're simplifying a lot of these is to make expressions easier to work with. And we also have to note, too, that from time to time we'll encounter an expression that can't have a value equal to 0 in the denominator. So anytime that we do simplify these expressions, in the back of our mind we should be thinking about numbers that are off limits, or numbers that can't be used in the denominator, what we would call excluded values. So let's wrap up this video with one more example. I'm going to try to utilize an additional trick when it comes to simplifying. I'm going to look for a GCF in both the numerator and the denominator if it exists, but I don't think there is one in the denominator. I'm just going to use regular factoring in the denominator. In the numerator, there's a GCF. Certainly the number 2 can divide both of those terms, but you may notice that these two terms are kind of backwards. They're in reverse order, what we're used to. So in this case, I'm going to use the negative 2 as my GCF. This is a trick we learned a couple weeks ago, and that allows us to effectively reverse the order here. 8 factored by negative 2 leaves us with a negative 4, but negative 2x factored by negative 2 leaves us with a positive x. So if I pull that negative 2 out front, then that effectively reverses the order, and we now have a group x minus 4. We do this fairly often because if we're lucky, we're going to see this exact factor in our denominator. Let's check it out. In the denominator, we're dealing with a standard trinomial with a equal to 1, so I know that x has to be placed here at the beginning of each of those groups. And then if I look for two numbers that multiply to make 16 that also add or subtract to equal negative 8, I think my only choices are 4 and 4, more specifically a negative 4 with a negative 4. At this point, you should notice that we've got a pair of terms, two terms separated by a multiplication sign in the numerator, and a pair of terms separated by a multiplication sign in the denominator. Terms that are separated by a multiplication sign can factor if they exist in the numerator and the denominator. So this x minus 4 term or group can factor one of the x minus 4 terms or groups in the denominator. Now it can only go 1 for 1 here. 1 from the top can take 1 from the bottom, but it cannot take 2 of these terms from the bottom. With those gone, we would now note that our simplified fraction is negative 2 over x minus 4. And this expression would likely be a little bit easier to work with than the original expression that we had. The nice thing is that these two expressions are equivalent. The only difference is that one's been simplified compared to the other. And another thing that we should be worried about are excluded values, or numbers that are off limits. But we will worry more about that tomorrow. We'll get into a more specific description of them tomorrow. In the meantime, I hope this helps our discussion a little bit. If you have concerns or questions, please let me know, and we'll talk to you later in class. Thanks for watching.